All right, welcome to another IAEI News Live. This is a recorded session because I'm here at the IAEI Western Section meeting, and I am right down the hallway from the R&R Ranch. And if you've never been to a Western Section meeting before, if you ever get there, you need to get to the R&R Ranch. Today's discussion is going to be around an example that was given to me by a friend of mine, an electrical inspector, who had a question, and we're going to walk through a real world example, and I'm going to use this moving forward. So let's just get to it, and it all starts now. All right. Okay, welcome back. And I'm laughing because it's pretty noisy out there, and I am pretty far away from the R&R Ranch. So anyway, we're having a great time here. The Western Section meeting has just started. I'm recording this Sunday night. Tomorrow starts our program. We have some really great talent coming in. Each of the code making panel members are going to be speaking on code making panel changes for the 2023 code changes. And we're going to be working on Tuesday morning. We have a 6:30 a.m. education committee meeting, which I chair for the Western Section. And we're going to be talking about the program for next year. So get your ideas and thoughts in, and make sure you get West by God, Virginia on your calendar for next year's IAEI meeting. We're going to have a great time in West Virginia. Oglebay Park is where we're going to be. If you've never been to the beautiful state of West Virginia, you're not going to want to miss next year's IAEI Western Section meeting. All right, so I want to show you. I want to show you what I was. This example was shared with me by a friend of mine, a mentor of mine, and he called me about this project. And you might look at this and say, well, it's a typical service, but it's not. This is not the service on this structure. This is a feeder. This right here is a feeder that is supplying power through a switch. Whoa. So you have a feeder that basically comes in, comes down to a switch, and comes back out and feeds this transformer. And let me tell you what I want to do. I want to walk through this example. This is a real world example, and I'll just share with you that. So I get a phone call about a simple question. And it's one of those questions where you go, I want to bounce something off of somebody. So this gentleman calls me, sends me this picture, calls me, and because I had other questions, he sends me a series of pictures that really helps put things in the frame so you understand how to answer and how to dialogue through this application. Picture's worth 1,000 words. So he sends me a picture, and as we walked through this example, it was very clear that this is a very good example that you could spend hours on in teaching the fundamentals of the National Electrical Code and how to put things together. There are a lot of articles and a lot of sections that play a role in this application. Now, as I told you, upstream, I'm going to erase that real quick, but upstream, up here, I'm going to erase it again. If I draw, and what the heck, I think I can do this. There we go. I got it back. So if I continue this up, away from this building is a circuit breaker. So you have a circuit breaker that is feeding this transformer through a switch, and all of this is outside. So we know it's a wet location. Okay, so we know that this is a wet location. So everything out here has to be listed for a wet location, right? So that's one of the little fundamental things we can't forget about the application. So all of these have to be your 3R enclosures, etc. All your fittings, right? So if you looked at all of these fittings down here, all of these fittings have to be listed for the application. And all of these, anything that is a connecting point has to be listed for a wet location. So don't, so now you get into, I'm just going to get rid of some of this stuff. Now you just get into the concept of just the equipment that you're picking. And if you think about it from a specification perspective, you got to make sure you specify the correct products for the application. It's a dry type transformer, obviously. So we come in here. So I'm just going to draw it like this, and we come out and we go into a fusible switch, right? We go into a fusible switch, then we come out of this fusible switch and we go into a trough. And we get into the tap rules, because I believe if I am correct here, those conductors in that trough are 250. So this is a 250 MCM cable, and these are 100 amp switches. And the conductors that are in each of these are 2 American wire gauge, 2 AWG. Okay, so that's sort of the layout. Now, and I have a better little one-line diagram, but I just want to talk about this a little bit, because I just want to walk through the example, and I'm going to show you why I think this example, from a classroom perspective, from an education perspective, is just a gold mine. And I will. And my plan is to just use this as long as I can and go into depth on a little bit of every part of this application. So we know all of this equipment okay, we know all of this equipment is feeder equipment, right? So that is a feeder, because that feeder is fed from the service equipment on the other side of the building. We know this is just a switch, non-fused, right? So what do we have to think about from a non-fused switch perspective? We have to understand available fault currents, short circuit current rating of that switch. This is a dry type transformer, and it is 480 to 208. Okay, and the impedance, I have the impedance on another diagram. So I come through this transformer, I come into a safety disconnect switch. So this is a fused switch, and we have to figure out what size fused switch that we need on there, and that's transformer basics. Okay, so you have a basic transformer. You have to determine the full load amps of the transformer. You have to figure out the size of the transformer secondary conductors, what the overcurrent device is on the secondary, what's that size that you want to put in there. Then on the primary, that breaker that's over there in the service panel that's feeding this transformer through that safety switch, you've got to figure out what size of breaker is that main breaker on the line side. So you have basic fundamentals of transformers. Article 450, you're in 215 for feeders, right? You're in Article 215 for feeders. So we have 215. We have Article 240, because over here, I mean, just in general from an overcurrent protection perspective, but after this fuse switch, what they do is they tap off and they come up into this switch. They come back down and go out. They tap off of this, come up through a fusible switch, come back down through that pipe, and down through that, down out to, I believe these are like individual dwelling, I think they're dwelling units. So you have the tap rules that you've got to think about. Right, so we got the tap rules. We have Article 215. We have Article 240. We have Article 250. Right, 250 for grounding and bonding, because you got to think about this is a separately derived system. Okay, that is a separately derived system. So we have to think about we got to think about where is it bonded, right? So if you look at this transformer, I think I have a better picture on the next page. Yeah, right here. Okay, there's a ground rod right here. That's your grounding electrode. And then this is your grounding electrode conductor. Okay, so that tells me that my bonding, the bonding of my neutral, my grounding electrode conductor, and I'm going to call this the grounded conductor, and my equipment grounding conductor is all done in the transformer. So that means that I have a supply side bonding jumper inside of this panel. So you're getting now into the you're now getting into Article 250, 250.28, 250.30 for the grounding electrode, the sizing of the grounding electrode. I believe that's 250.30A5. I think 4 is the grounding electrode, 5 is the sizing of the grounding electrode. Then you got 250.52, your grounding electrode conductor. You have 250.66, that's your sizing of your grounding electrode conductor. You have the bonding jumpers in 250.102. You got your supply side bonding jumper, 250.102 Charlie, I think it is. What else? What else do you got over here? So you could do an entire session just on proper grounding and bonding. You have flex here. How do I make sure that this equipment is bonded with that equipment? Do I have to put a conductor inside that raceway? Do I have to do how do I handle this over here? How do I handle the bonding with all of these switches, right? So this session gets you into grounding, it gets you into bonding, it gets you into feeders and feeder protection, transformers. So what else? What other articles you got? You've got 215, you've got 250, you got 240, you have 450 for transformers. You got switches. Switches. What is that? 404. 404. Man, I always get 404 and 408 mixed up. I think it is 404, but you know what? I'm going to double check. Hold on. Let me, I know, and you know what? So, shameless plug for NFPA. NFPA link. If you do not have NFPA link, I'm telling you, you got to get it. I've been using it more and more and more recently, and I'll tell you what, I absolutely have fallen in love with NFPA link for a lot of different reasons. I can search this. So what was I looking for? Oh, chapter 4, I think it's 404 switches. I doubted myself, but that's okay. It's always good to just make sure you have it right. All right, so okay, so pencil. All right, now here's even a better picture. There we go. Look at this picture. Look at that. Okay, so there is your grounding electrode. This is your grounding electrode conductor, right? You got a nice shot of your fittings, making sure that all of the right fittings are in place per the listing, and all of your bonding is done correctly. And oh, here's another good one. So this is the world we live in today. One of the reasons, just look at what you see on this installation. You have one manufacturer here. This is a, what is that? That is a, oh my goodness, I can't remember the manufacturer. Anyway, this is a different manufacturer. We'll call it X. This is a Schneider. These are Siemens. Okay, so what's the issue that we're having right now in our marketplace, in our industry? We have product, or we don't have product. It's hard to get some products, hard to get panel boards, hard to get circuit breakers, all this good stuff. So what this electrical contractor decided to do was to make this installation with what he had or she had, which was possibly from different manufacturers because of trying to get product these days. So you've got a little bit of a mix and match, which tells you the strength of standards. When products are listed to a standard, there is a base level of performance. We're talking switches here, we're talking transformers, we're talking, well, basically switches. I mean, you got 1, 2, 3, 4, 5, 6 switches. One's a non-fuse switch. This is a fuse switch, and these are fuse switch. So a whole mess of different types of products, which again gives you an example of just what you might find on job sites, which is, mixing and matching some products is not a bad thing, technically. All right, so this is the installation. Now, I drew a diagram, there, this is it, of what's going on in this application. Now, one of the questions that this, now I'm just going to couch this at that. When you look and I show, oh geez, when I show this bonding here and here, that's not the way it is. And I have a picture of the trough, but I'm just showing that from a diagram perspective to help you understand that it's all bonded together. Okay. Now, let's start up here in the transformer. We have a delta Y transformer. We've got a delta Y ground. And remember I told you that the bonding of the neutral, the grounded conductor, is bonded with the equipment grounding conductor, is bonded with the grounding electrode conductor, which gets you to the grounding electrode. So what differentiates that separately derived system is where you're bonding all of this, all of these aspects from a grounded conductor, an equipment grounding conductor, and how you treat all that. And we always ground in one spot. Now, the picture, okay, so this picture shows I've got a ground rod, right? So what's the questions? Do I need two? Should I, instead of driving a ground rod, I've got a structure right there. Should I be tying that in with the structure's grounding electrode system? And if I drive ground rods, should I be tying the grounding electrode system for the building, the structure, in with this ground rod? So these are other areas that you need to think about, right? So the grounding electrodes, this is a class unto itself, 1 hour. And my thoughts are, I'm going to grab some industry, maybe get some of the IAEI's panel members from panel 5, and sit down and talk just about the grounding of this installation and bonding, because there's more than an hour of grounding and bonding right here. You could live in Article 250, talk about the separately derived system. How do I treat this? How do I treat this grounding electrode? This building, this structure has its own grounding electrode system. And what does Article 250 tell us? I have to use all of it for that. Well, should I be tying this transformer into that? That's a discussion point. I'm not getting into the details in this session. Okay, I'm not going to get into all of the details and all of the answers. I'm setting the stage, because moving forward, you're going to see this example, and we're going to walk through the grounding and bonding of all of this. We're going to walk through the transformer, primary protection, secondary protection, the conductor sizes, the available fault currents. We'll calculate the incident energy at the safety disconnect switch and at each of these 100 amp switches. And at that trough, we're going to use this and we're going to abuse it and make a really cool series of videos to just walk through. And I'm going to need your help to make us accurate. Okay, share your knowledge. I showed this picture, and I'm going to walk. So I came to the western section, and I showed this image and a few others to some people out in the lobby. I mean, I just checked in. People are checking in, and I had my iPad open, and I was like, "Hey, take a look at this." And I was asking some questions, and oh my goodness, I tell you, I had more and more people around me looking at this photo and the series of photos and pointing at issues. One person brought up the fact that they're driving a ground rod. Is it one, or do you need to have two? And oh, by the way, you've got a building right here. Shouldn't you be tying it into the grounding electrode system of that? That was one of the comments. What were the other ones? Let's take a look at some of the pictures. All right, look, I even the 1/4 inch gap. So this piece of equipment has a beveled edge. Whoop, right in here. That's beveled, and what's that bevel supposed to do is give you a 1/4 inch gap in between the enclosure and the wall. And the one person I was talking to said, I don't know about this brick and how this looks. I think I'd check that gap, make sure it's got a 1/4 inch. The other gentleman looked at these screws on this and said, hey, that's a self-tapping screw. And based upon the head, I don't know if I can get rid of that. Hold on. It's, just based upon what that head looks like. Whoops. They said that's a self-tapping screw. Well, I don't know. Is it a self-tapping screw? I can't tell by looking at the top of a screw. But these guys here, they could. What else in here? So that was 1/4 inch screw, self-tapping screw. How about this one? This is in those 100 amp switches. Is that a self-tapping screw? You're not allowed, right? We need to have so many threads, and there's an article and a section that tells us how many threads we're supposed to use. Put that in the chat. I'm counting on you. What section of the code tells me how many threads I need engaged for a bond for this grounding? What was the other one? So no ground on that one. Oh, what else? All right. So anyway, I'm telling you, these types of examples are great teaching tools. So you have this transformer, right? So we've got a 75 kVA transformer. We have 480 to 208 volts. We have 4.65% impedance. Now we can do a lot with that. I can calculate the full load amps on the primary, the full load amps on the secondary. So full load amps on primary and secondary. Let's do that. All right, so 75 kVA divided by, we'll do the secondary first, divided by the square root of 3, divided by the kV on the secondary, 0.208, equals what? Get your calculators out. All right. 75. 3 square root divide 0.208 divide 208.2 amps. So that is full load amps on the secondary. 208 amps. All right, so how do I get the full load amps on the primary? I can do one of two different things. I could take 208.2 times 208 divided by 480. What is that? 208 times 480 divide, I get 90.2 amps. Now let's do it the long way. 75 kVA divided by the square root of 3 divided by 0.480 is 75. 3 square root 0.48, 90.2 amps. 90.2, 90.2. Two different ways to get to the same number. One, I just used the turns ratio, 208 over 480 of the transformer to reflect the secondary current to the primary, and I got 90.2. The second way is to do the standard equation. Take the kVA divided by the square root of 3 divided by the kV, and I get 90.2 amps. Now the next piece of information that you could use at the starting point here is the available short circuit current. So how do I do an infinite bus calculation? What was the impedance? So there's your data. I've got a 75 kVA, 4.65% impedance. So remember that number, 4.65. There's my voltages on a primary and secondary. Those are the important information that you need. So 4.65. I take the secondary full load amps, which was 208.2, divided by the percent impedance. What was the number? 4.65? 4.65. Whoa. 4.65. So I do 4.65, and then I multiply that by 100. So get your handy dandy calculator out. 208.2, 4.65 divide, 100 divide. Hold on. Erase this. 0.2, 100. 0.0465. Oh, no, that was right. Yeah. I see, sometimes I double guess myself. I don't know why. Times 100 equals 208.2. 4.65 divide 100 times 208.2. I keep missing the 8.2. 4.65 divide 100 times 4,477 amps. So what does that tell you? That tells you that all of this 4.65. I just want to double check. 75.208 divide 3 square root divide 208.1792. And then I divide that by 0.0465 is 4,476 amps. So 4,000, I'm going to write it 4.5 kiloamps. That's what's available at the secondary of that transformer. So any equipment downstream can be rated 10K, which is pretty much your default. I don't have to worry about any of that equipment from a short circuit current rating perspective. Circuit breakers and fuses, I'm covered. I can get the 10K circuit breakers, no worries. So that helps me now short circuit current rating 110.10. All right. So you're into 110.10, helping somebody understand the short circuit current rating. Marking of available fault currents on panel boards, etc. That's in 408. No, not 408. See, for some reason, with me, I don't know how you all are, but panel boards, switchboards, 408. Yeah, it did 408, and I don't know why I questioned myself. 408. So in 408 tells you need to mark the available fault currents, right? So do you see how this example can branch off into many different areas for teaching and helping people understand how the National Electrical Code relates? Now, here was the other question that we had. You'll notice now in this light blue, you'll notice I bond everything up here. Then I don't bond it in this switch, the neutral, the grounded conductor. I bond all of my equipment grounding conductors for bonding and whatnot, but I don't bond my grounded conductor. That passes through and it comes down into the trough. And if you remember where the trough is, it's right here. Right? So in the trough, there's my three-phase conductors going into these power distribution blocks. And then my neutral comes over to this Polaris, whatever, multi-tap, whatever. I don't know what I think I just call them a Polaris, but I don't know if that's a brand name. But anyway, all of my neutrals are tied together. Now, what they did not do, there's the switch. This is the 100 amp switch. You'll notice there are two hots. There's two hots in here. Two hots going in, two hots coming out. There's an equipment grounding conductor pulled up in through the raceway and bonding through this, what we think is a tap screw, a self-tapping screw, which would be illegal. And you'll notice they plugged the holes. They had a conduit there. They plugged that hole. So good job, right? Very good, neat installation. And you've got the marking for line. Anything that's marked line and load cannot be reverse fed. What else? So there's no grounded conductor here. So they basically, if I look at the one line diagram, they just switched the leg. It's a single phase. So they took the hot conductors up for single phase, took it through the 100 amp switch, back down, and then they picked up the neutral and the equipment grounding conductor and went down to the, I guess they're individual dwelling units. Now, the question that a few people had was, do you have to pull the grounded conductor? Do you have to take this conductor up into this switch, even though you're not going to use it? Is there a requirement in the code that requires you to pull that conductor up into that switch? And as far as I can find, and that's why you got the 404 up here, because I looked in 215, I looked for feeders, I looked in 250 for grounding, I didn't look at 404 for switches, and the only thing that's in 404, and if you remember, this is a little code, I guess, history, there is a requirement for switches that feed lighting. And I've got to find the location. There it is, 404.2c. And 404.2c, I remember when that requirement went in the code. Here was the concern. In residential applications, we were seeing switches. How do we do a light switch? We'd bring two hots down, break the circuit. We'd bring the equipment grounding conductor, but we wouldn't bring the neutral. We just switch the hot leg of the circuit. And what was happening was that light switch would be there, and eventually somebody would say, hey, I want to put in a occupancy sensor. And when they put an occupancy sensor in, there's no grounded conductor, and the occupancy sensor needs to be powered. And how do you power it? You power it between hot and neutral. But there's no neutral down in that light switch. So what did they do? And even listed them this way. They connected the equipment grounding conductor to the light switch. And what is that doing? It's intentionally putting current on the equipment grounding conductor, although it's milliamps. But those are called objectionable currents. Go into Article 250 and tell me down in the chat, in the comment section on this video. I know it's recorded, but put in the chat, in the comment section, what section in Article 250 tells you you cannot have objectionable currents on the equipment grounding conductor. That requirement, it was an electrical inspector drove that change, saying he would not permit the use of those occupancy sensing switches, because they would use the equipment grounding conductor. He required you to pull a neutral and properly wire that switch between hot and neutral to power the switch to do your controls. So they changed the National Electrical Code. I can't remember what cycle it was, and if you know, put that down in the chat. Come on, let's make it happen. They said that the grounded conductor for controlled lighting circuits shall be installed at the location where switches control lighting loads that are supplied by a grounded general purpose branch circuit serving bathrooms, hallways, stairways, and habitable rooms or occupiable spaces as defined in the applicable building code. And it says where multiple switch locations control the same lighting load, such that the entire floor area of the room or space is visible from the single or combined switch locations, the grounded circuit conductor shall only be required at one location. It says a grounded conductor should not be required to be installed at lighting switch locations under any of the following conditions. It gives you 4. And the grounded conductor shall be extended to any switch location as necessary and shall be connected to switching devices that require line and neutral voltage to operate the electronics of the switch in the standby mode and shall meet the requirements of 404.22. So this goes into the code. So that's one location where you have to pull the grounded conductor to the switch. Where's the other location where you have to pull the grounded conductor? That's at your service, right? The service from the utility, they'll tell you, even if you're not going to use it, you need that grounded conductor there. So there's a few locations over on dryers. I think it's in 422. Check me out. For dryer circuits, you're required to have that neutral, that grounded conductor. So because why? Because of the light that they started putting in dryers. You know, you open the door and there's a little light that comes on and shows you. Well, how are they powering that light if they weren't pulling a neutral to the appliance? They were powering it over the equipment grounding conductor. And although it wasn't GFCI protected back then, if it was, it would have been tripping GFCIs left and right. But it was violating Article 250. Okay, this is the cool stuff about the code. This is what you learn at these meetings. I tell you what, I was very uneducated when it comes to the National Electrical Code, and I came to my first IAEI meeting. I think it was the Ohio chapter, if I'm not mistaken, and I will never forget. I had my little booth outside, and I was shaking hands. I was cutting wire with ASCIs. I was actually, demonstrating arc fault circuit interrupters with the guillotine. If you've never seen that, it's really cool. But when we did it, it was so, oh, I'm even going to go how unsafe it was. But anyway, we would cut wire and demonstrate that a thermal mag breaker would not trip and an AFCI would trip and explain the technology. And I would, and after break, we would go into the meeting room and sit and watch the educational program. And I would sit there and I would listen to them talk about raceways. I didn't have anything to do with raceways. They would talk about services and feeders, and they would talk about switches and panel boards and switchboards. And they would get into all of these little details. And I'll tell you what, every one of it was going over my head. There were individuals that got up to that microphone and were rattling off article numbers and section numbers. And I used to just look at them in awe. And I would talk to these guys and gals, and I would ask them questions. And I would say, where does it say this? And they would say, oh, that's an article, whatever. And it's in section, well, and sometimes they would go, well, it's either going to be section this or section that, or somewhere in that ballpark. And I would just be absolutely amazed. And I have been going to these IAEI meetings, and when I look at a drawing like this, and I can go, oh, that's Article 215, and well, this isn't Article 230 because that's not a service. It's Article 215 for feeders, and if that's outside, then it's 225 for outdoor feeders. And can't forget about Article 250 for grounding and bonding and sizing of that equipment grounding conductor. And you got to think about Article 200. I could not do that before. It took a lot of time listening and walking through applications like this and trying to answer questions. That's why I love our Q&A sessions. At these section meetings and at chapter meetings, we do Q&A sessions where we'll ask the question, you try to answer the question. We'll have a person who's up on stage who will give the answer to the question, and then we debate what they just said. It is absolutely unbelievably phenomenal. And if you've never experienced it, you need to experience it. It's great to watch videos, but you need to get to these meetings in person, shake hands. There are people at this Western section that are way smarter than me. And I absolutely, you want to grow in your knowledge, surround yourself with people who are smarter than you. And if you think you're the smartest person in the room, then you could just go home. You never want to be the smartest person in the room. You always, and everybody has something to offer. And this is a really good example. So I tell you what, so pulling that neutral up into each of these switches, we came to the conclusion that you do not have to pull that neutral, that grounded conductor into each of these 100 amp switches. And that just pulling that switch leg up there, those two conductors through those two fuses, is all you need to do. Because that neutral is not going to do anything anyway. You're not doing anything with it. And you're not going to put a light switch there. And the requirement back in 404 is for light switches. It's not a 230. These aren't service devices. So you don't need that neutral. Then what else? Okay, so that was the neutral question. All right, so what this project has, this was actually a 400 amp switch in real life. It's a 400 amp switch with 400 amp fuses in it, but I can't do the 400 amp fuses. Why? Because I've got 250 MCM. Right? So then I absolutely love it. I love it so much I draw my pen. Okay, I'm back. All right, so then the one individual out here in the lobby, he says, well, wait a second. Who did the load study? Because what if that 250, because I have what? I have a 100 amp switch, 100 amp switch, 100 amp switch, 100 amp switch. And if you look at the picture, let's take a look at the picture. Okay. I have 100 amp switch, 100 amp switch, 100 amp switch, 100 amp switch. So there's 400 amps worth. Now, granted, I might not be using all 100 amps on that, but I also got another panel board over here. And that's what that is. I'm waiting on the photo of that, and I'm hoping to get the photo of the inside of that transformer because I want to show the bonding and everything. But anyway, there's another panel board here. So the one, and where are my loads? My loads are here, 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 and here that go to those units, and up here that go to whatever that goes to. So his question was, when they did the load calculation, is that 250 MCM conductor, is that the right size? Should it be a 400? I don't know. Could it be a 400? Well, let's think about that. What's the secondary full load amps? Secondary full load amps. We did the calculation. Remember, what was it? 208.2. What, 1.75? 1.75, 208.2, 364. I can go to the next higher, 400 amp. So I could put a 400 amp switch on the secondary, which is what they did, right? They put a 400 amp switch in here with 400 amp fuses, but they only put 250 MCM. And what's the ampacity of 250 MCM? What section do we go to in the National Electrical Code? What article we go to first? So when you want to navigate the National Electrical Code, you got to think, well, we know Chapter 3 is wiring methods and materials, so that's Chapter 3. We know it's 310 for conductors for general wiring, and then we know 310.16 is our ampacities, and we have our table 310.16. So that's how we navigate to the right. And then we have to use 75-degree C column. All right, because we're landing on switches. And actually, we're landing on a switch. We're landing on that 400 amp switch with it has a 400 amp fuse, but what is 250 worth? 250 is 255 amps worth of conductor ampacity. I can't put a 400 amp fuse on 250 MCM. So I would have to go up to like a 600 or whatnot, or maybe two of those. Whatever. I'd have to address my issue with ampacity, right? So, I mean, could it possibly get any better? Yes, it can. Okay. I love this stuff. Article. Now let's go to article. No, remember what we're doing here. I have a 250 MCM conductor. I have a 250 MCM conductor. Then I come off of my 250 MCM conductor with a number 2. Well, we'll do it this way. 2 AWG. Now, and there's that now, and this is, say, protected by a 250 amp fuse. Because remember, I mean, we're still in the phase of, hey, the 400 ain't cutting it. So you have to protect this conductor at its ampacity, and I believe that's at was it 250? Hold on, 250. I can't remember the ampacity. 250 MCM, 255 amps. So 250 amp fuse. So I put a 250 amp fuse, but a number 2. A number 2 is around 115 amps, if I'm not mistaken. Yep, 115 amps. So and I have a 100 amp, and then I go out, right? So this is a tap conductor, and it's not. So here's another thing that we started talking, and this is when the pictures came to me. Because when he explained it, I was thinking that secondary conductor was a transformer secondary conductor, and you can't tap a tap, but I've got a fusible switch on the very secondary of this transformer. So I'm not tapping a tap because the tap is occurring on the secondary of this. I'm tapping a feeder. So then where do we go for feeder taps? And we have to understand the tap rules. What's the length of the conductor that I'm permitted to have tapping in on that feeder, on this feeder? What's the length of the conductor that I can have that's going up to here to this fusible switch, from here to here? That's in Article 240, overcurrent protection. And you have the tap rules. And my computer is a little slow. My computer is a little slow. I don't know why. All right, 240.92, I believe it is. Feeder. Okay, here we go. Feeder taps. Now it finally comes through. It's an outside feeder tap. Okay. That's transformer secondary conductors. That's so, and that this would be the transformer secondary conductor. What is over there is not a transformer secondary conductor. So you get into all of your, you're basically looking at 10 foot to make sure that you are within your 10-foot length for that tap conductor. But put the section number, put the reference numbers in for your tap conductors. Okay, so your tap's not over 10 foot. So this would be 240.21b. I'll give you that one. 240.21b1, tap's not over 10 foot. If the length of the tap conductor does not exceed 10 foot and the tap conductors comply with all the following: the ampacity of the tap conductors not less than the combined calculated loads, not less than the rating of the equipment that it's connected to. The tap conductors don't extend beyond the switchboard, switchgear, panel board, disconnecting means. What is that? It's a disconnecting means or control. So what does this tap conductor do? Right? This tap conductor, so I have a conductor here. I tap it, I bring it up, and I land on the high side of that fusible switch, and that's the length of the tap. Because everything past the tap is a feeder. So remember, I have a fuse right there. That fuse is providing protection. Now I'm into a separate feeder. My tap is only from where I've tapped in here and up. And if we look at the trough, where does my tap start? My tap starts right, my tap starts right here. That's where the power distribution block. The length of this conductor, the length of that conductor that goes down and it goes up all the way to the line side, I don't want that to exceed 10 feet. And it can't go outside, except at the point of connection to the feeder, the tap. Okay, and then there's the 25-foot rule. So the other thing you could use this for, which is cool, is to help people understand the different tap rules that are out there. And when do I have to use the 10-foot? When can I use the 25-foot? Then there's the transformer secondary, taps over 25 foot long, outside taps, unlimited length, where the conductors are located outside of a building or structure, except at the point of load termination, and comply with all of the following. The tap conductors are protected from physical damage. These are. The tap conductors terminate at a single circuit breaker or in a single set of fuses. These do. The overcurrent device for the tap conductors is an integral part of a disconnecting means or shall be located immediately adjacent thereto. The disconnecting means for the tap conductors is installed at a readily accessible location complying with one of the following: outside of a building, these do, inside nearest the point of entrance of the tap conductors, or C, where installed in accordance with 230.6 nearest the point of entrance of the tap conductor. So outside taps, can they be unlimited length? There's another option, another area to explore, and we will explore the tap rules with regard to this installation. We are going to have a blast talking about this installation. If you think about just in this short hour that we quickly went through, we hit 215, we hit 110, we hit 110, we hit 215, possibly 225, we hit 250, 240 for overcurrent protection and tap rules. We had 404 for switches. We had 450 for transformers. What else could we possibly put on this We talked about the screws and the distances in the back. So that's your enclosures. I can't remember article. There's just a lot of opportunity screaming at you right on this diagram. So get this diagram, take and freeze frame this picture, take a snapshot of it. Okay, I'm going to give you that permission. Take a snapshot of this and walk through the different sections of the code, different articles. Talk about the power distribution blocks. They have a 110.10 short circuit current rating. How do I know? Now, the secondary fault current here was 4,000 some amps. So, but go through the exercise. What is the short circuit current rating of a power distribution block? Where do you find that information? Talk about the types of screws that you're allowed to use in these applications. Look at all of these fittings. Are they the right fittings? This is PVC. What does that tell you? David Williams and I talked. He says, well, they're using PVC going into the ground. Obviously, they don't have a lot of movement in this location where this is at, right? So in some locations, you can't use the PVC going into the ground location. So think about those applications. In the switch, right? So they're using the outer two legs of the switch. Why are they using the outer two legs? Is that what the manufacturer tells you? What's the reason for that? How about the grounding and that screw? How many threads am I supposed to have? How about this fitting down here? Where in the code does it tell you what those fittings need to be? How about where in the code does it tell you to plug those holes? How about NFPA 70E? And we didn't even get into the arc flash analysis of all this. So if you're looking for examples to help educate on the National Electrical Code, sometimes you don't have to go that far. You can take a picture like this. When you're doing an inspection, if you're a contractor, take pictures of it at different stages too of installation and use that to help educate those who are coming into our industry, engineers, contractors, electricians, apprentices, journeymen. Help them understand these installations, understand the details of the National Electrical Code and how we're following it and how we have to meet those codes because they're adopted in our states and jurisdictions. Hopefully, if you're in those areas that do adopt the code. It's amazing, absolutely amazing what you learn. All right, so I hope you got something out of today's session, and I hope to see you at a section meeting one day. I wish you were here at the Western section, and maybe you are. And well, if you are, you shouldn't be watching this live because we would be doing it would be, no, I'm an hour behind. So 12 o'clock, it would be 11 o'clock Eastern. This is on 12 o'clock Eastern. We're in the central time zone here. And you, if you're at the Western section meeting, you should be learning about the activities of Code Making Panel 2 right now. What happened in Panel 2. Because what we're doing first is we're going to have code Q&A. We have a code panel of experts answering questions. And then after that, that's 2 hours of that. Then we're going to get into about a half an hour of Code Making Panel 2. We're going to go have lunch. And then after lunch, we have Larry Eyre and David Williams, correlating committee. Larry Eyre is the correlating committee chair. And we have David Williams, who's on the correlating committee for the IAEI. And they're going to talk about what's going on with the correlating committee, what's happened in this code cycle for the 2023 cycle. And I think Larry might share a little bit about the vision of what is to come later in much later years of the development of the National Electrical Code. All right, so I think I beat up my hour, and hopefully we will see you at a section meeting in the future or a chapter meeting. If you ever get down to the West Virginia chapter, you got to ring us up and come down and watch our programs and get involved with the West Virginia chapter. We would love to have you at one of our chapter meetings here in West by God, Virginia. So thank you for listening for an hour of me rambling. And the R&R Ranch is right through that door and about 100 feet down that way. And I can hear them. I don't know if you can, but they are loud. And they're talking code in that room, and they're building relationships, they're having fun, they're talking about home and family and sports and the Pittsburgh Steelers. Everybody's a Steelers fan. And we're just enjoying company with each other and building a network of relationships that are going to propel us through our careers. I'm telling you, it helped me, and it can help you too. And hopefully, again, one day I will see you at one of these section meetings. So thank you for joining us. Thanks for what you do for the electrical industry. Thanks for what you do for IAEI. If you're an IAEI member and you contribute, and especially if you're a board member on one of these many different chapters that we have globally, thank you for what you do for your fellow electrical professionals. We need more people like you out there to take leadership roles. So if there's anyone out there who wants to be a leader in the electrical industry, please let me know. We'll get you engaged with the boards or the chapters that you're involved with, and we will all succeed together. And I'm telling you, you will learn and you will love it the more and more you dig into this thing we call electricity. All right. From the IAEI News Live, I want to thank you for joining us. Thomas Dimitrovich here. Take care, stay safe, God bless, and please stay healthy. See you next Tuesday.